In infrared spectroscopy, the type of infrared radiation that is absorbed by bonds in a molecule is not expressed in units of wavelength, it's not expressed in units of frequency, or even in units of energy. It is expressed in units of wave number. Wave number is calculated by taking the frequency of the radiation and dividing it by the speed of light. If you recall, the frequency of radiation has units of 1/second. The speed of light has units of meters per second. And so mathematically, the wave number has units of 1/meters. Now for infrared radiation, the size of the wave number, the magnitude of the number here, it works out best if wave number is converted to units of 1/centimeter. And again, that's just due to the size of the value of these wave numbers. 1/centimeters, or we often write that as inverse centimeter, centimeter to the -1. These are the units that are used to report the data in infrared spectroscopy. In this video, I just want to give you some context to wave number to help you understand a little bit about what it represents. Let's begin by thinking about how wave number is calculated. Remember, it is the frequency over the speed of light. For a frequency, when we have, for example, a type of radiation that has a low frequency, this means that it has a low energy as well. Due to the formula E = h nu, we know that the energy of radiation and the frequency of radiation are directly proportional to each other. So if the energy is low, the frequency is low. If the energy is high, the frequency is high as well. And then from this equation right here, we can see that wave number and frequency are also proportional to each other. So this means if we have a low frequency, which also means that we have low energy, we can also say that we have a low wave number. So looking at any infrared spectrum, we know that the portion of the graph where we have a low wave number, this is the portion of the graph that corresponds to low energy. And the portion of the graph where we have high wave number, this is the portion that corresponds to high energy. So let's make a list of some of the different types of bonds that correspond to high energy radiation or high wave number infrared. And we're going to write it over here on the left-hand side because the left-hand side is the high energy, high wave number area of the spectrum. And let's also make a list of some of the types of bonds that are associated with low energy or low wave number. And we're going to put that on the right-hand side also because this is the side, the right side is the side of low wave number. High energy bonds are bonds, as you can imagine, they are bonds that are very strong bonds, and they're also, we like to call them very tight bonds. In chemistry, we model a bond as being like two atoms that are sort of connected on like a spring. This is a really good analogy to use in infrared because in infrared we're talking about, the stretching and the movement of this particular bond. So a high energy bond is one that is very strong and it's also very tight in terms of it doesn't have a lot of flexibility, it doesn't stretch or bend or flop around very easily. Strong and tight bonds are, of course, triple bonds, very, very strong bonds, and double bonds, which are also pretty strong, although not as strong as the triple bonds. And then we also see that strong and tight bonds are going to be bonds to light atoms or small atoms. In organic chemistry, this would specifically be bonds to hydrogen, the smallest and lightest out of all of the atoms. In contrast, low energy bonds are ones that are going to be pretty weak and also what we call as being loose bonds. So these loose bonds are ones where it's very easy for the bonds to stretch or bend around quite a bit. And these weak, loose bonds are going to be single bonds, and they are also going to be bonds to heavy atoms. On an infrared spectrum, we can use this sort of generalization to get an idea about what types of bonds appear at different places on the spectrum. So if our low energy area are the single bonds, bonds to heavy atoms, we could kind of make a note that this end of the spectrum here is where we expect to find our single bonds, whereas over here on this side of the spectrum, this is where we expect to see our strong, tight bonds. So specifically on the very far left side of the spectrum, this is where we see our bonds to hydrogen atoms. And next to that, pretty close to that, this is where we see our triple bonds. In general, there are going to be some exceptions to this. And then in the middle here, this is where we usually see our double bonds.